Okay, so let's start with the reflection, or the first property of light that we will talk about in geometrical optics will be the reflection. So what is the reflection? Let's know what is the behavior of light when it hit a reflex, or it hit a surface. So reflection, or the reflection of light, depends on, or what are one of the properties of light that occur when the light hit a surface. So if we have an interface like this, and then the light is hit this interface, so it is transferred from, this is the first medium and this is the second medium. So this can be anything like air, like water, or any other medium. This second medium again can be anything like air, like water, like glass, like everything. So what is the property of light when it hit this interface? So if this is an incident light over this interface, so it could be either absorbed within the interface. So this interface can absorb some light, or the light can be transmitted through it, which we will call later refraction, or the light can be reflected from this interface, or it bounces back from the first medium, and this what will we call the reflection. So again, the light will have different behaviors when it hit interface. It is either absorbed through this interface, or it can reflect back from this interface, which is called reflection, or it can be transmitted through this interface, which we call refraction. So reflection is important in our lives, meaning that if an interface that is completely transparent, you will not be able to see it. So like this lady, she is hitting on the glass because she wasn't able to see it. Although this is reflection, this reflection over the glass, this what will make you able to see it. If this reflection is not present, you will see this glass completely transparent, and you will not be able to appreciate the presence of it. So let's start talking about the laws, and laws meaning that there are certain rules that govern the reflection and other properties of light when it hit interface. So we'll start by laws of reflection, then we'll talk about the laws of refraction, and then we'll go to the rules that govern the reflection in the prisms. So let's start to concentrate about the laws, and this what will make us able to understand the behavior of light. So if we have a reflecting surface like here, and there will be a perpendicular meridian or perpendicular line over this reflecting surface, this will be called the normal. So the normal is the perpendicular line over the reflecting surface. If we have an incident light that is hit the reflecting surface, then it will form an angle with the normal. It is called the angle of incidence. After this, the light will be reflected, and the angle between the reflected light and the normal, it's called the angle of reflection. The law of reflection is that the angle of incidence equals the angle of reflection. The angle of incidence can be, we can say that the angle of incidence is I, and the angle of reflection is R, so I equals R. This is called the law of reflection. It's as simple as this. So what happens when the light is hitting an irregular surface? When the light is hitting a regular surface, it undergoes reflection in different directions. So it undergoes a scattering. This scattered light will lead to a visualization of this irregular surface. For example, if we have this furniture, and there is light coming from the window, and this light will hit this furniture and reflect in different directions. And once you see this light, you will be able to see this furniture. So by diffuse reflections, most objects are being appreciated, or most objects are visible. This is except for the self-luminous one, like a bulb of light. This is not the rule in such case. But what happens if the reflecting surface is not irregular? So for example, if we have a perfect reflecting surface like this, the surface of water here, so this surface of the sea is, you will not, and that is free of irregularities, and there will no diffuse reflection here. The reflecting surface here itself will not be visible, so you will not be able to see the reflecting surface, but you can see the images on this reflected surface. So the image of these balloons can be seen by reflection in the surface. So you can't see the surface of the sea, but you can see only the reflected images over it. So this happens when you have a completely perfect reflecting surface. When we have a transparent medium or transparent material that is completely regular and completely free of irregularities, then the type of reflection here is not the diffuse reflection, but we call it the specular reflection. And this method of reflection will enable us to see this transparent material, and this the specular reflection is the mode of examination of the corneal endothelium and other transparent material that we will say in the instruments. So here is the diffuse reflection, and you can see that the light is reflected in different directions. However, in case of a specular reflection, the light is reflected in the parallel direction and in regular pattern. So this will be the difference between the specular reflection and diffuse reflection. Now let's study, or let's know, what are the characters and the properties of images when are reflected by either a plane surface, like a plane mirror, or by a curved surface, like a convex mirror or a concave mirror. First of all, let's start by the reflection of plane surface. So if we have a plane mirror like here, and we have an object, this object will project light rays over this plane mirror, and then the light will be reflected according to the law of reflection. So this is the incident light, and this is the normal, and this is the reflected light. So the angle of incidence will be equal to the angle of reflection. So if we have our eyes at this direction, and this is the eye, can the eye see the image? The answer is no. Or can the eye can see the object here? The answer is no, because the eyes cannot see in broken lines. So the light can, or the eye can't track the object like from the incident ray to the reflected ray, and we cannot see the object by this way. So how can we see, or what can we see? We can see the image of the object by just the extension of rays that extended from the eyes inside the plane mirror. So we can see the object, or can see the image of the object by extension of the direct extension of light rays inside the image. So you will now can see the image of this object that is reflected on the mirror, and the eye can see, or the brain can assume an image by just extension of the light rays. So again, the brain is trained to see the reflection or the extension of light rays. So this is an image inside the plane mirror that is not an object, and you can see the object itself. You can, if you are looking at the mirror, you can see the virtual image inside the mirror that is made by extension of rays. So again, let's have another example. If we have an object here, and this is the source of light, this source of light will project light inside the object, and the object by diffuse reflection will cause reflection and scattering of light in all directions. Some of these lights will hit the mirror and will be reflected according to the laws of reflection to hit the eye. So what can the eye see? The eye can see not the object, but it can see the image. And they can see the image along the direction of extension of the light rays. So it can see an image inside the mirror. This image is called eye, and the object is called O. And this image is virtual, meaning that it is not a real image. So it is because geometrically a real image is formed by the actual light rays, but virtual image is formed by the extension of light rays. So this is from the geometrical point of view. From practical point of view, a virtual image cannot perceived or captured on a screen. However, the real image can be captured on a screen. This will be the difference, practically speaking, between the image, whether it is virtual or it is real. So here we have we need the most important thing here, or the most important notes to illustrate is the character of each image formed by each surface. So we need to understand and to know what are the characters of image constructed by light rays in case of plane mirror, or in case of curved mirror like a concave or convex, and also in the lenses. So we need to know what are the characters formed by the convex lens and the concave lenses. So this is what the geometrical optics is all about. So if we have here a plane mirror, and always note that in optics, the mirror has a reflecting surface and a dim surface or an opaque surface. So we have here, and this usually this or always the reflecting surface will be toward the object, and you can see that these lines or these parallel oblique lines are always toward the non-reflecting surface. So by checking these oblique and this oblique parallel short lines, you will be able to know where is the reflecting surface. So we know that the reflecting surface here on the left. So if we have here an object, and this object now there is some light over this object, and this light is by diffuse reflection hit the mirror, and some of these lights are now projected or reflected toward the eye. And now by extending the lines or the reflected ray, we'll now see a virtual image inside the image, inside the mirror. So what are the characters of this virtual image? First of all, it is upright or erect. So the head is up and the foot are down, or the feet are down, and this will be the same case in the image. Also, the second thing that it is virtual, because it cannot be captured on a screen, and it is formed by the extension of the light rays. Also, it is laterally inverted, meaning that you can see here that the singer is the microphone in his left hand, but on the image you can see that the microphone in his right hand. So the image is inverted or laterally inverted. The image lying perpendicular to the reflecting surface, so it is not oblique, but it is perpendicular over the reflecting surface. And the distance between the object and the reflecting mirror is the same like the distance between the virtual image and the reflecting mirror. So both objects and the virtual image are on the same distance from the reflecting mirror. So these are the characters of image formed by the reflecting mirror or the plane mirror. So I'm saying that there are candidates who cannot watch the video. So unfortunately, this is usually a problem with your internet connection at your country. So sometimes your internet connection block the video or the block the screen sharing from other countries. So you need to check with your internet service provider. Okay, let's now talk about the rotation of the plane mirror. If we have a plane mirror and we rotate it, what will be the character of reflected ray? So if, for example, let's say that we have a mirror which is called M1, and there is an incident light ray which is the eye. This incident ray will be reflected, forming the R1 or the reflected ray 1. This will be along the perpendicular meridian or along the normal, which is the N1. So by laws of reflection, the angle of incidence will be equal of the angle of reflection. So what happens if we rotate this mirror? If we rotate the mirror one like this, So it will become mirror 2, and the N2 or the normal will change in position. So what will be the effect of the reflected ray 2? So the angle of rotation between the normal of the mirror 1 and the normal of the mirror 2 will have a relation between it and between the angle of reflection. So the angle of reflection between the R1 and R2 will equal double the angle of rotation between N1 and N2. So again, if a plane mirror is rotated while the light is incident upon the center of rotation, the reflected ray, which is R2, is deviated through an angle equal to the twice of the angle of rotation of the mirror. So this will be the effect of rotation of a plane mirror. So is everything clear up till now? Okay. Now let's talk about the spherical mirror. So what are the rules of spherical mirrors? The plane mirror will be the easiest one. So there are more details regarding the spherical mirrors for the convex and the concave mirrors. So let's start first to have some basic information about the shape and the anatomy of the spherical mirror. So what is a spherical mirror? Spherical mirror means simply it is a part of a sphere. So if we have like this ball, and this ball, we cut a surface, assume that this ball is reflecting, or the surface of this ball is reflecting. So if we cut a part from this sphere, this part now is called a spherical mirror. Note that the central part or the center point of this ball is called the center of curvature. So again, this is having a spherical mirror. So what will be the type of this spherical mirror? Is it a convex or concave? And how can we determine the reflecting surface? So if we have, this is a mirror, or this is a reflecting sphere, and we cut a part of it to have a mirror. So if the reflecting surface is from the outside, this is called a convex mirror. If the reflecting surface is from the inside, it is called the concave mirror. So here we have, this is a concave mirror. So we can see this black line points to the non-reflecting surface, and this is the reflecting surface of the mirror. So this is called a concave mirror. If we have this is the non-reflecting surface. Let me make a pen, it will be better. So here is the reflecting surface, and here is the reflecting surface. So this is called a concave mirror, and this is called a convex mirror. As we said, let's start to have some information about the mirrors. What are the anatomy of it, and what are the terminology? So we need to know some information about the language that we are using to talk about the mirrors. So for a mirror, it is taken from a sphere, or this sphere, the reflecting sphere has a center of curvature. So it is point to, or can be illustrated by letter C. So C is the center of curvature, or the center of sphere from which this mirror is taken from. So you can see that this is a convex mirror because the reflecting surface is from outside, like here. And this is a concave mirror because the reflecting surface is from inside. And this is C, or the center of curvature, which is the center of the sphere from which this mirror is taken from. Then we have the P. P is the center of the mirror. So center of the sphere is C, center of the mirror is P, or the pool of the mirror. If we have a line that connects the C to the P, then this is called the radius of curvature. So the radius of curvature is the line extending from the C, or the center of curvature, to the P, or the pool of the lens. Sorry, this is I just got confused. The line between C and P is the called the principal axis. So sorry for that. The radius of curvature is just any line passing from the center of curvature, and it is perpendicular over the sphere, over the lens. So this is called the radius of curvature. So the radius of curvature, or the radius of a sphere from which the mirror is apart, like here, this is called the radius of curvature. And sometimes, as long as it can pass also through the pool of the lens, and can be also equal to the principal axis. So the principal axis is the line joining the curvature and the pool of the lens. So here is this line is called the principal axis, which is a line passing through the center of curvature and the pool of the lens. If any line passing from the center of curvature to the mirror, then this line is called the radius of curvature. If we have any line passing through the center of curvature other than the principal axis, like this one, then this is called a subsidiary axis. So it is not the principal axis because it doesn't pass through the pool, but it passes to any line or any surface of the lens different from the pool of the lens. Then we have another important point that is called the principal focus. Focus of everything, meaning that it is the point at which the parallel rays will come to after reflection or refraction by a surface. Meaning that if we have a concave mirror like here, and there is some parallel lines that will hit this reflecting surface, this reflecting surface or will make the light rays converge in case of concave mirror, or convex or diverge in case of convex mirror. So in either cases, the light ray will be convergent or divergent to one point. This point is called the focus. The focus can be either real, meaning that can be made by a true ray, like here in concave mirror, or it can be virtual. So it can be made by virtual rays, like we can see here. So in convex mirror, the focus is virtual, and in such condition of concave mirror, the light rays or the focus is real. So again, this is a point of intersection of parallel rays after they are reflected from the mirror. The focal length is the distance between the center of curvature, like here, and the principal focus, which equal half of radius of curvature. So as we said before, this is the radius of curvature, which is the distance between the center of curvature to any point on the reflecting surface. So the F is located midway between the center of curvature and the pole of the lens. So the focal length, this is the focal length, which equal half of the radius of curvature. This is the first rule in case of lenses. So sorry, the mirrors. So the first rule here again, that the focal length equals half of the radius of curvature of any reflecting surface. This is very important. So please remember it at your mind until we get back to it at the end of reflection when we are discussing the rules. So what is the character of image that is formed by the mirror? It's either convex or concave. So the image that is made by the concave mirror is real. So if we have here an object, this after reflection from this concave mirror, it will form a true image. This image can be or a real image. This image can be captured on a screen because it is formed by real rays. However, in case of convex mirror, the light rays or the image is formed by extension of rays or formed by virtual rays. That's why it is a virtual image and cannot be captured on a screen. You may wonder what is meant by captured on a screen. So if we have a screen like here, and then the light, and you will be able to see this, the reflection of this man over the screen. However, if you put a screen here, you will not see the reflection of the this man in the screen. This is meant by, what is meant by captured on screen in case of true image, or a real image and the virtual image. Now let's know how to construct an image. So in order to draw, or as we're talking about the geometric optics, so we need to know what are the rules that we will follow in order to construct images reflected by the mirrors. So we have three rules. Let's start first with the first rule. A ray parallel to the principal axis, and it will be reflected to or away from the principal focus. So any light ray that is parallel to the principal axis will be reflected to pass within the principal focus, like here. So this is the principal axis, this is the center of curvature, and this is the focus. This is the radius of curvature, and this is the focal length. So if we have a line or a light ray that is parallel to the surface, it will bounce back or reflect from the reflecting surface, and it will pass into the focus. This can be either converging to the focus in case of a concave mirror, or diverging from the focus like this, and its extension will be passing into the focus on the other side. So this will what will happen in case of convex mirror. The next rule is that when the light ray passing through the focus, it will the light ray will passing through the focus, and then it will hit the reflecting surface. It will bounce back parallel to the surface or parallel to the principal axis. So again, when the light passing through the F or passing through the principal focus, it will be reflecting back, and when it reflects back, it will reflect parallel to the principal axis. So it will be like the reverse from the first condition. The third condition, or the third rule, is that when the light is passing through the center of curvature and then it hit the reflecting surface, it will be reflected on its own path. So it will be reflected on the reverse direction. So to summarize, let me just remove these drawings. So to summarize, we have a light parallel to the principal axis will be reflected passing through the focus. If a line passing through the focus, it will be reflected parallel to the principal meridian, and if a line passing through the center of curvature, it will be reflected upon itself. So this is the behavior of light as it is as it hit the reflecting surface. So in order to construct the image, we need at least two lines. So if two lines are intersecting, then we can construct an image. So we don't need that these three lines to be intersecting in order to form an image. So how can we describe an image? We said the characters of image in case of plane mirror. So what is the character of image in case of the concave and convex mirror? We need to know what is its location in relation to the mirror. We need to know how big it is. We need to know what is the location. We need to know what its size. It is either enlarged or diminished in size. What is its orientation? It is upright or upside down. And what is its nature? Is it a real image or is it a virtual image? Like here, for example, this is the mirror, and here we can see an object. And this object, by constructing rays, you can see that there is a light ray passing through the focus, and then it will reflect parallel to the principal meridian. And then there is a light passing through the center of curvature, and then now it is reflected upon itself. So the object here is formed, or this image is formed by extension or these virtual rays. So what is the character of this image? This image is behind the lens or behind the mirror, as you can see, and it is virtual. It is as it is made by virtual rays. It is erect because the head of arrow is up in the upright position as the same as the object, and it is larger in size. So you can see that the object here or the image here is larger than the object. So this is what is meant by the characters of the image. So let's begin. What are the characters of images formed by the concave lens? If we have here a concave lens, the character of the image will depend on mainly on the location of the object. So for example, if we have a far object which is beyond the center of curvature, so where shall the image be constructed? Let's draw our rays. So there will be a parallel ray to the principal meridian that will reflect pass through the focus, and there is another light ray will pass through the focus so that it can be reflected parallel to the principal meridian. So point of intersection between both of them will be the location of the image. So since the image here is from the flame of this candle, so this should be the position of the image. So here it will be also the flame of this candle, and you can see that the image is inverted. So the first of all, what is the location? The location is between C and F. And what is it real or virtual? It is real. It is made by the actual rays. Is it upright or inverted? It is inverted, as you can see. And as you can see also, it is smaller than the object. So these are the characters of images when the object is placed beyond the center of curvature. If the object is placed at the center of curvature, so what will be the characters of the image? Again, we construct our rays and we can find that they will intersect at the center of curvature as well, but just below the object. So the image will be formed as center of curvature, and it is real, it is inverted, and it is of the same size as the object. So if we want to obtain an image that has the same size like an object, we just place the object in the center of curvature. If we bring the object closer to the mirror so that we can place it now between the center of curvature and between the focus. So what happens? You can see that we construct our rays. So parallel ray will be reflected passing through the focus, and another ray will pass through the focus and will be reflected parallel to the principal axis. And now we have the image is formed by intersection beyond the center of curvature. So it will be outside C. And since this image now is formed by actual rays, so it is real, it is inverted as well because it is below the principal axis and it is larger than the object. So these are the characters of image if the object is located between C and F. Let's bring the object closer. So if we bring the object closer at the F, so we have now a light passing through parallel to the principal axis, and it will reflect toward the focus. So it will pass through the focus, and we can't pass a line that is passing through the focus. So we will construct another light ray, which is the light ray passing through the center of curvature. So if we have like the lens like extended like this, and we have another ray that is passing through the center of curvature, so it will be like this, it will reflect upon itself. So it will pass through the center of curvature. So what is happening now, and what will be the character of image? There will be no image formed because the reflected rays will be parallel to each other. So whether it is the one passing through the focus or the one passing through the center of curvature, both of them are parallel together. So image can be said it is no image formed or at infinity. So if we place the object at F, then the image will be at infinity. Let's now move to the object more closer. So it will be inside F. So it will be inside the focus of this concave mirror. So let's construct our image. One ray will be parallel to the principal meridian, and then will pass through the focus. And another light ray will pass through the focus. So it will be like this, and we can be extended to the focus. And now it can reflect parallel to the principal meridian like this. So you can see that the light rays are diverging on the left side of the screen. So there will be no image formed at the left side of the screen like here. However, the light rays, if we extend them on the right side of the screen toward the opaque part of the mirror, then both of them can intersect. So both of them can intersect to form an image behind the lens. So since it is behind the lens, it will be a virtual image. This virtual image is upright, as you can see, and magnified. So if we want to use a convex mirror or a concave mirror in order to have a magnified virtual image, we just put the object inside the focal length of this mirror. So these are the characters of images constructed or formed by the concave mirror that will depend mainly on the position of this object in relation to the concave mirror. So what is the image formed by the convex mirror? So we have only two rules, whether we have only two positions of the image, whether it is inside the F or at F. So if the image inside F, like here, so this is the object, and this is the principal axis, and this is the convex mirror. And let's construct our rays. So we have a right rays parallel to the axis, parallel to the principal axis, that will be reflected from the surface of the lens. And in such condition, the extension of light rays will pass into the focus. And we said that the focus, it is not only in one side of the lens, but in both sides. So it will be on the same, like here and like here, and the center of curvature can be like here and like here. So the light rays can be extended to pass through the focus, and another light ray will pass through the center of curvature like this, and it will be reflected upon itself, as we can see here. So the light rays again will be diverging on the side of the reflecting surface. However, their extension can be joined together or can be intersecting to form an image. This image is behind the lens, and it is virtual because it's formed by virtual rays. It is diminished in size, or it is smaller in size, and inside the focal length of this mirror. So if the object is inside the F, then or if the image, whatever the position of the object, always the image will be smaller and erect and virtual inside the focal length of the mirror. The only exception is if the object is at infinity. So if the object is at infinity, so any object or anything coming from the infinity, light rays from it will be parallel. So as we said, any reflecting surface and any parallel rays hitting a reflecting surface, light rays will always come to a focus. So if the parallel rays hit the convex mirror, the light or the image will be formed at the focus. Other than this, if the object is placed at any location in relation to the convex mirror, then the image always will be placed inside F, which will be smaller in size, and a virtual image and erect image. I hope that this is clear. We will talk now about the side mirror. Yes, that's right. No, for the side mirror, it is convex, and for the headlight, it will be concave. So if we have here a concave mirror, so we have here the fog light, And the fog light is meant to spread the light for large distances so that you can see the road in front of you. So how this can be placed? This will be this by placing the bulb of light like here in the focus of this lens or in the f of this lens, so that the light will be emerging parallel so that you can see the road in front of you. So in case of the fog light of the or the headlight of the car, the light bulb is placed in the focus, and the light rays will be reflecting in the concave mirror inside this headlights, so that it will illuminate the road in front of you by this parallel rays. Also can be used as a magnifier. So this man's face can be seen magnified, and these candles can be also seen magnified because these objects are placed inside F. So we said if we have an object inside F, this will lead to a virtual, it will lead to a magnified image that is beyond the C or beyond the center of curvature. So what is the application of the convex mirror? It will be the reverse. The side mirrors of the car is of convex mirror. And why is this? Because we need the object to be smaller. So if we have a smaller object, we will now can see a large field of view. So for example, if we have here a plane mirror, a normal plane mirror in the sidecar, you can see that there is magnified images. So you can see the grass here and you can see the grass here, but you can't see large field of view. But if we substitute it with a convex mirror, you will have a smaller image. So you see the grass becomes smaller, and this grass also becomes smaller, and you have been able to see larger view. So you can see this house, and you can see these trees, and you haven't been able to see this tree before. So the convex mirror make or form a small virtual image. So this is me in Edinburgh. You can see that I have become dwarf all of a sudden because I'm standing in front of a convex mirror, like in a street in Edinburgh that's full of mirrors. So you can just show some funny shapes of you made by this mirrors. So the convex mirror, as you can see here, make small virtual image. Okay, so let's talk about some rules that will govern the mirrors, or the rules that will govern the reflection at mirrors. First of all, how can we calculate the power of the mirror? Let's start with some very, very basic and important rules in optics. The focal length or the focal length of any reflecting surface will be equal of radius of curvature divided over 2, as we said from a while. We said that the radius of curvature is just double the focal length, or the focal length is half of the radius of curvature. So we can formulate it like F equals half of radius of curvature. Then we have the power. A power of any surface is equal of 1 divided by the focal length. This is the most and first basic rule in optics. Power of any reflecting surface or refracting surface equals the 1 divided over the focal length. So it will be this, or the inverse of the focal length. So if we substitute the F by half R, so it will be equal 1 divided by 1 or half R. So this will be equal to the 2 over R, or 2 divided over R. So again, P, or the power of any reflecting surface, will be equal to 2 divided over R, or 2 over the radius of curvature. So if we have a concave mirror, the power of this concave mirror will be equal 2 divided by R. And if we have a convex mirror, it will be 2 divided by R, but note that the sign here is minus, because the convex mirror will form a virtual image behind the lens, and this is what we talk about now. The distance. So what will be the distance? How can we calculate the distance of object or distance of image in regard to the lens? This can be done by the rule, which is 1 over v small plus 1 over u small equals 1 over f. So what is or what are the v and u and f? Which, as we said, 1 over f equals 2 divided by r. So v is the distance of image from the mirror. So 1 over the distance of image from the mirror equals or plus 1 over u. So u will be the distance of image from the mirror equals 1 over the focal length equals 2 over the radius of curvature. So this is the second rule here, which will govern the distance of the image and distance of object. So if we have this is like an equation. So if you have two variables, you will be able to calculate the third one. So if you have v and u, you will be able to know the focal length of the lens, and also you by multiplying it by 2, you will able to know the radius of curvature. If you have the focal length and radius of curvature, and you know the distance of the object, you will be able to know the distance of the image. So this is like a mathematical equation that you need to understand to be able to calculate the distance of any object or image from the mirror. Then we have the magnification. So magnification equals or magnification, the rule of magnification of the lens. If you want to know what is the ratio of magnification of any mirror, this can be calculated by a ratio. This ratio is I divided by O equals V divided by U. So we know now the V and know U. So what is the I and what is the O? I is the magnification or the image size, while the O is the object size. So this is just logic. If you want to know the magnification of anything, you just compare the relation between the size of the image to the size of the object. So for example, if the size of the image is double the size of the object, so you say that the magnification is 2 or 2 times. If the magnification of the image is becoming small, so for example, it is half of the size of the object, so the magnification become 0.5% or half of the object size. So this is the logic, but the new rule or the new thing here is that it can be also equal to the distance of image divided by the distance of the object. So the image size over the object size is equal the distance of the image over the distance of object. So this is the third rule that governs the reflection. I hope that it is clear. Finally, here we can see that this is the same man again that show a smaller image. So the ratio of or the magnification of this mirror can be either calculated by knowing the image size over the object size, which will be again equal to the distance of the image divided by the distance of the object. Also, in the case of convex mirror, so the magnification of this convex mirror is by knowing or by dividing the image size over the object size, which will be the same ratio of the distance of image divided by the distance of object. When doing the mathematical calculations, we know we need to respect the sign conversion rule. So the sign conversion meaning that there are some rules in math that will control the image that is formed by the reflecting surface. So whether this surface is a mirror or it is a lens, we need to respect the sign of this image or this object in relation to this lens. So how can this be done? First of all, the all distance are measured from the pole of the mirror which is the central part of the mirror, or the vertex of the lens, which is the central part of the lens, to the point of question. For example, if we have here, like this is the mirror or lens, so this is the principal axis, and this is the principal plane, and they both intersect at a principal point in case of mirror, or intersect as the vertex of the lens, as we will say later. So all measures or all distance are always measured from the left. So we always, in case of mathematical optics, we calculate the distance from the left to the right. So we always assume that the light rays is coming from the left to right. So distance are measured in the same direction of the incident light. So if I have an image or an object that is constructed by light rays that are formed from a light ray that pass from the left to right, like for example, like here, and formed like this. So this can have the plus sign. If we have an image that is formed by light rays against the direction of light, which will be from right to left, like this, it will have the minus sign. So if we have like for example, like a light ray here, or an image here, or an object here that is formed by light rays coming from right to left, then this should take the minus sign. If we have an erect image or upright image that's above the principal axis, then it should take the plus sign. And the reverse, if we have an inverted image that is that is below the principal axis, it should take the minus sign. So these are important rules when you are drawing an image, or you are drawing or constructing an object and image using the light rays. So for example, let's say an example, if we have, for example, if we have this is a lens or a concave lens, and this is an object. This object now is placed on the left side of the principal axis, or the principal plane, so it can take the plus sign as it is everted and erect. If we have now an image that is formed by the reflected rays, which is now this reflected rays from right to left, then it should take the minus sign. And this minus sign due to is that the light ray is reflected, and that the light ray also, or the image also, is below the principal axis. The clinical applications of mirrors, so we have different applications like a concave mirror and different applications for convex mirrors. So in order to converge light rays, we need concave mirrors. And this can be utilized in different ophthalmic equipment like retinoscopy and direct ophthalmoscopy and indirect ophthalmoscopy. Beginning of lecture, as we go through the optics, each lecture will be dependent on the previous lecture. So when we are talking about the instruments, we will just collect what we have said in geometrical and physical and human optics in order to construct these machines and know how they work. So when I say to you that the retinoscopy has a concave mirror, so you will automatically know that this concave mirror will cause convergence of light rays. Direct ophthalmoscopy and indirect ophthalmoscopy also can use the concave mirrors. Convex mirror have just more limited uses, because they usually tend to diverge light rays. So they are used in the keratometer, which is again will be discussed in the instruments section, and the catoptric images, which will be discussed in a while. So what is the catoptric images? Catoptric images or Purkinje-Sanson images are just simply, they are the images formed by the reflecting surface of the eye. So if we have here the cornea and we have here the lens, so when light rays enter the cornea and lens, they will be reflected. So there will be some light rays that reflected from the anterior corneal surface, light rays that, like here, and light rays that will be reflected from the posterior corneal surface. There will be light rays reflected from the anterior lens surface and light rays reflected from the posterior lens surface. So Purkinje-Sanson images or catoptric images are 4 images that are formed by the 4 reflecting surfaces of the eye. We need to know what are the characters of each image. So image 1 and 2 and 3 from the anterior and posterior corneal surface and the anterior lens surface are all erect virtual images because they are formed by convex reflecting surface. So the anterior corneal surface is convex, posterior corneal surface is convex, anterior lens surface is convex, so they act as convex mirrors, so they will form a virtual erect image. This is in contrast to the posterior lens surface, which is the image number 4. Image number 4 is formed by a concave surface. This concave surface is forming a real inverted image because it is act as a concave mirror. So the posterior corneal surface, or the posterior lens surface is forming a real and inverted image. So what is the clinical application of these images? Image 1 is the most clinically used clinically used application of Purkinje-Sanson image. So it can be used in different devices. There is an old device that was invented like about more than 100 years ago, which is the Placido disc. Placido disc is a ring or a concentric alternating dark and white rings. Then these rings were used to project on the cornea to have an idea about the corneal surface. Is it regular, like in this eye, or irregular? So we can see there is distortion of these rings. So how can we know that there is a regular or irregular cornea? It is by reflection of this Placido disc over the surface of the cornea, and this will utilize the Purkinje-Sanson image 1, as this image will be reflected from the anterior corneal surface. The second application will be the keratometer. So it is used for measuring the radius of cornea. We will not go through this now because this is like half of a lecture, and it will be discussed in the instruments. And second thing we will discuss today when we will talk about the prisms is the Hirschberg test. So the Hirschberg test, or the pupillary light reflex, is a test that is used to measure the angle of squint. So by knowing the reflection of the central light, or by projecting a light in front of the eyes and seeing the central pupillary light reflex, we will know if the central light reflex is central, so we will know that the eye is orthophoric, or there is no squint. Or if we can see here like this eye, the light reflex is more toward the nasal edge of the eye, so this is the eye is deviated outward, so this eye has a squint. And this is called the Hirschberg test, and this is based on the image formed by the light on the anterior corneal surface. For the image 3 and 4, these are used to study changes in lens during accommodation. So image 3 is present in the anterior lens surface, and image 4 is present in the posterior lens surface. So these images are separated by the thickness of lens, which is increased during accommodation due to bulge of the lens.